this. What on earth are they? We'll identify a function as not just a function now, it may be even. So called an even function. So what's so special about it? Or it's an odd function. Now guys, these are definitions. First, even. Must fit this definition. Then I'll tell you what this all means. F of a negative x is equal to f of x. If your function satisfies that statement, not only is it a function, it's an even function. And something sort of special happens with it. This means you go to your function, and I'm asking you for an example that maybe you can come up with. You go to the function, replace x with a negative x. Do it, and all of a sudden it leads you right back to where you started. It takes you right back into the original function. Now, can anyone name a function that right now, based on what we've done, that might satisfy this brief definition?
X squared.
Come again.
X squared.
X squared. That's the most basic one. That is an even function. And to show for sure by that definition, if I take f of a negative x, which means replace x with a negative x, squared, it takes me right back to where I started. So if these two match up, it's even. Name one word for me that you might think in your mind that if I do the same thing I just did, it's also even. In fact, I have one or a couple here that I want to point out to you guys for a reason, but can someone name one for me that maybe besides x squared that you might say, Professor, I can think of another function that if I do this business, is satisfied. And therefore it's an even function.
X to the power of 4.
X to the 4th, right? X to the 6th, X to the 8th. Now don't be misled. Are there some functions out there that may not give you that hint that if this is an even exponent, 2, 4, 6, 8, definitely those are even. Are there some others out there that may not look like that and they may turn out to be even? What do you think?
Absolute value.
I'll throw that in. F of x is equal to absolute value x. If I test it here by that definition, if I take f of a negative x, which means with her function, replace x with a negative x. Guys, please tell me, what do you think absolute value of a negative x inside there, would that really take me right back to the original function? Could I say that's equivalent to this, which was the original function? Do you think these two guys are the same that she just gave me to work with? Do you think those two statements are the same? For example, if I replace x, it's just a random with a number like 4. If I put a 4 in here, this is negative 4. What's the absolute value of a negative 4? 4. If I put a 4 here, what's the absolute value of just 4? 4. Do they match up? A negative number maybe, a negative 6, put a negative 6 in here. Negative, a negative 6 turns into a 6. Absolute value is 6. If I put a negative 6 down here for the x, I get 6 again. They match up. So that can be recognized also as an even function. Now, to go into chapter 3, gradually, I brought this one in and tried to identify it as an even function and do something with it that's going to help me move into chapter 3. And guys, I brought this one in. Yeah, it looks nice. F of x on the side here is this. X to the 4th subtract 9x squared. Now you may say, Professor, you threw another one at us that has even exponents. And therefore, I would think, even without the check on the definition, it's going to be an even function. If I take f of a negative x, turns into f of x, the original function, it's even, Professor. It is even. Now I'd like to sketch it. It's going to be an even function. I'd like to sketch it. Now, can someone give me a hint as to, as I gradually move into chapter 3, which chapter 3 is all about graphing, Anyone give me an idea what you might want to do first if now they ask you to sketch this even function? What might you do? Anyone? Thank you. Looks like a little factoring first. Maybe rewrite this as what? X squared times x squared subtract what? 9? True, guys? Put a y here. Can I factor further? Will x squared subtract 9, difference of squares, break down further into what? X subtract 3 and x plus 3. Now watch carefully. You've been with me long enough where I try to get all this math to relate. There should be something there that we've done before. We did the factoring, of course. But now if I go to the grid and ask you, okay, now what can I do with that factoring over there to get, let's say, a sketch? Anyone have an idea? Do it again.
X-intercept?
I can find the x-intercept from right here. Seems like on that last exam I asked you guys to find x-intercepts, didn't I? And to find x-intercept, you replace y by 0. If I do, it now looks like this. And Ignacio, if I split these up with your help there, and set each one of these factors equal to 0, which I definitely can do, look at this. You end up with x equals 0, easily done. X equals 3, x is equal to a negative 3. Now I know my x-intercepts. Also, I could find what, the y-intercept? Which I don't think is going to be very exciting, but I'll find it. The y-intercept can be found always for any function. Take f at 0, replace the x's by 0. And guys, without me doing it, what am I going to get?
0.
0. So the x-intercept was 0, the y-intercept's also 0. But I know where they are, at least. So guys, if I go to my grid, I got this to work with. And also, let's go out to 3. Work with it. Negative 3. We have those. So I guess I connect those 3 and the graph is a straight line. So let's go ahead and connect them with a straight line. You know that's not linear. It's not a linear function. Yeah, I see a student doing something. Exactly. It's not linear. Now tell me something that we've done in class before that you probably did not realize at the time that might be helpful to see what the sketch looks like. Is it a parabola? I'll tell you ahead of time, it's not. Is it a straight line just connecting those points? It's not. It's not linear. In fact, it's a cubic. No, quartic. 4. Any ideas? And I see some students saying, Professor, I sort of look like that, but I've got to know a little scheme here. How can I find out what it really looks like? And show some work. Don't you dare go off to UCLA and ask you what to graph this, and you're in the audience and you do this. I say, I want to see the work. That's what can I do? I'll give you a hint. It's something we've done much of in this class that might help me to get the shape that I see students doing. What is it? Anyone? Let's tie all this math together. Should be shocked. What we got before? The method. Yes?
Plug in values to get points.
I can plug in values. Thank you. Susan, that's quick. Thank you, thank you, thank you. Thank you. I can plug in values. I'm looking for something else, so some vocabulary, some terminology that we've used in here. Probably day 1. No, probably day 1, day 2 that we met. We used it. In fact, you guys have used it on a quiz. Right on exam 1. That can now be applied here. What is it I'm looking for?
Plotting the values.
Tell me again.
Plotting the values.
No, that's what she said, plugging values. Not quite there yet. Something else. that we've done.
Quadratic formula?
Do it again.
Quadratic formula?
Not quadratic formula, because this thing's a 4. I can use quadratic formula maybe if this had been not a 4 here. Maybe an x squared something. I can use that quadratic formula only on quadratics. It's not a quadratic. What is it that we've done day 1 when I first met you? I'm pretty sure I did day 1. And if you had it on a quiz or an exam, you did it. What is it I'm looking for? That can now be applied here. Shame on you.
Sign analysis?
Sign analysis. Sign analysis. You go, wait, Professor, are you kidding? You choose a point here. You're going to choose a point here. You're going to choose a point here. And choose a point here. Remember, you sign analysis. Now, what you choose is up to you, of course, your test number, as always. Out to the left of -3, guys, I'm going to try -4. I'll say close by. In between, I'm going to try -1. Over here, I'm going to try a 2. And out to the right of 3, I think we'll try a 6. Sign analysis. Now here's the issue. When we use sign analysis, I'm using sign analysis, guys, on the factored form that we did way back on some equations back then. I'm trying -4. I'm just concerned about the sign. That's why they call it sign analysis. If I go back to here and replace x by -4, if I square a -4 for the first factor, that's 16, which is positive. If I replace -4 here in my second factor, it's a -7. Negative. -4 plus 3, negative. Now I got a positive and a negative multiplied together, which will give me altogether a positive. What do you think that positive is telling me? It told me something a little differently in previous work. What do you think it's telling me here? The portion of the graph on that side, since it came out to be positive, guess where the graph is located? It's above the x-axis. So what it looks like, I don't know right yet, but it's got a little curve to it. Not a straight line. I would say it looks like that. Now you can plot additional points if you wish, but I know it's above the x-axis. Now my next test number is -1. Okay, let's go back, guys. Replace x by -1. When you square it, positive. -1 subtract 3, negative. A -1 plus 3, positive. And looks like that altogether gives me a negative, which means my next piece in here should be where? Below. So this one connect and drops down below. How far down it goes, I don't know. You don't know. It's got to come back up and do something like that. It's below. Now we're on the other side. I'm trying my test number over here between these two, 0 and 3, to get 2. Okay, go back. 2 squared, of course, is 4, positive. 2 subtract 3, negative. 2 plus 3, positive. Did I do that correctly? Did I do those signs correctly? Now I think altogether that's what? Negative, which means it stays below. So right there between here and here, I tested, it stays below. So it might look something like this. Now to the right of 3, I'm trying to 6. So the 6 in here, 6 squared, of course, is 36. That's a positive. 6 subtract 3, positive. 6 plus 3 definitely is positive. And altogether that is a positive, which means finally out here on the end to the right of 3, my graph is where? Above. There's your graph of this, using sign analysis. Does it make sense the way we applied this? We found the x-intercept and we applied the sign analysis, see whether it's above or below, and that's a sketch. Now I know, and you know by this time, if you look from left to right, Guys, is there a local max somewhere on this graph? A local max? I know it's a Monday.
Zero.
A zero right here. Is that a local max? Is there an absolute max? No. Is there a local min?
Yes.
In here somewhere. It looks like it may match up the way the graph might be symmetric. It might match up and it repeats itself over here. So at least there is a local min. Is that true? Is there an absolute min?
Yes.
Is there an absolute min? Are these two locals also acting as, the way the graph looks, acting as also absolute? Are those the lowest of all? So these two right here are absolute mins, local mins also. We have a local max right here. Do we have an absolute max? No. All kinds of things I could ask you here on this. Now, you say, Professor, you said this moves me into chapter 3, eventually. It does. I think of a good way to do this. This one's finished. I love sign analysis though. Love sign analysis. It's powerful. How much it can do for us. This one's done though. The graph itself is done. Let me see if I can ask you anything else about the graph. Oh, of course I can see something wrong with the graph. See something else again? I can ask you. Take a look at the, good look at the graph and tell me something about the graph that we've also discussed in class here. We did the sign analysis. We have the graph. The graph itself might be something that we discussed before. What is it?
Rain.
In fact, you saw some type of it on the last exam that I just returned to you. Is there a reflection from one side to the other?
Well, we have the.
Whoa, is there a reflection from one side of the graph to the other?
There could be. Yes.
I tried to grow it. I think that sketch looks good.
Well,
It's not exactly
Yeah.
wrong, it's not precise. Now, when I say, does the graph reflect across the x-axis? In other words, does this piece right here, if I flip it over, does it become this piece? No. But if I take this piece on the left, this piece right here, and take it across the y-axis, in other words, reflected, across the y-axis, where'd I get the other piece? So if I take this piece, take it across the y-axis, reflected, where'd I get this? And vice versa. If I take this, reflect it to the y-axis, where'd I get this? So there is something called symmetry. So the graph is symmetric about the y-axis, not the x-axis.
But wouldn't we need to know the vertexes?
No.
No.
I'll tell you why here. Beautiful. He's concerned about professor. Can I somehow find those two turning points down? I'm going to call them turning points. They're not parabolas here. Could I find them? So let's not use vertex. Just say they're the mins. Professor, is there a way to find the mins? Those local mins? Mr. Park, Isuja, I'm taking them into calculus. Can you tell them what they're going to do in Math 7 when they finally get to Math 7? I'm not going to show you the little trick here. To find those local mins, what would you have to do? Come on, don't scare me.
Absolute.
Now here's the function. Here's the function. I've got the graph. Here's this picture. Now they're asking for,
The mins?
yes, Professor, is there some way I can find in this pre-calc course, before I get to calculus, a way to find this point right here might be out 1 1/2 down 2. Who knows? This one might be positive 1 1/2 down 2. Who knows? They're wondering, can I find precisely where those points are down there and name them? There we go. Isuja, tell them what, when they finally reach Math 7, are they going to do that we're not going to do here? That's it. Do what? Yeah, they're going to take a derivative. You say, what's a derivative? You're not going to know. That's why I'm do Math 7. I'm going to set you up. Take a derivative, and then do what with it after you take the derivative of this? You see, Mr. Mathematician, what are you going to do after you take that derivative? No, Mr. Park.
Well,
Now,
we
Ms.
look,
Park, you're in math 11, 13, 15, which one are you in?
13 and 11. So,
Oh.
so we take the derivative and equal to 0.
You said equal to 0. And solve it. And after you do that, take a derivative. If you know how to find a derivative, which I'm not going to show you here, that's not part of the course. You take the derivative, you set equal to 0, since you asked, and you can find precisely where these points are. That takes calculus. So I'm not going to do it here.
They're gonna be the same though.
They will be the same. Sometimes they are and sometimes they're not. It all depends on the function.
So if we don't know if they're the same.
I got you, exactly. You say, Professor, then the symmetric might be off a little bit.
Yeah, it might not be. the same.
Exactly. No, looks like these two will be. Mr. Park, do me a favor. Go ahead and take the derivative of this mess, this function. Set it equal to 0 and see what it is. Real quickly for me. I threw that together just today. He's going to do it for you. Check and see.
Thank you. Mr.
They're,
Park.
absolutely, I'm glad you brought this up. See if these two are the same. Okay? Okay, guys, it's an even function. There's this picture. Looks like it's going to be symmetric through the y-axis, one side of the y to the other side of the y. And then pretty soon he's going to find exactly where those points are down there. Glad you brought that up. Take a little calculus here. Now, with that said, let me step back and look at it. Here we go. I'm going to give you another function, f of x. As he's doing this one. And this looks like this. X cubed subtract 4x. This is a cubic. Now first, do you think that's going to be an odd function? Can I identify it as odd? This last one was even. Mr. Park, you got that already?
Yeah.
Did it come out to be strange numbers or are they nice, well behaved?
It's actually 0, 3, -3.
-3, -3?
Yeah, and 0.
Wait, so this dropped down to -3 here. Mr. Park.
Maybe I'm wrong, but I got
Oh,
0.
don't you dare mess up. I know you're a teacher. I know you're a professor. I just talked to her today. And you got an exam last week.
Yeah.
I need to talk to her. I need to talk to her. Okay. Mr. Park, can you graph this for me?
Yeah.
And I'm doing this right here. Can you go ahead and graph this function for me and see if you can maybe find on the graphing what these 2 points are? That's what he wants to know. Okay, guys, let's run to this one. This one looks like it might be, what, even, odd, or neither? Looks like it's going to be odd. I see some odd exponents. And that's not always a giveaway. It looks like it's going to be odd. I will test it, guys, first for odd, and the odd functions definition, where was it? Did I erase it? Or do I have it yet? No, I have it yet. Here it goes. Odd function. And we think this one might be, we haven't tested yet. Definition, f of negative x, look at this, guys, start the same way as you do even, but you do not end up with the same function you started out with, like this one did. You end up with this. The opposite of the original. So if you can satisfy that definition, it's considered an odd function, and it has a particular shape to it. There's something going on. Now, most students will say, Professor, you jump into it, give me an example. Most students will say, try this one. Has an odd exponent. And since it has an odd exponent, maybe it's an odd function. We're going to test it. I test it by this definition. Take f of a negative x, which reminds me of x being replaced by a negative x. And then simplify that. Is that true, guys? F of a negative x, replace x by negative x in the function, which I did. If I cube this, we all know it's this. Now, is this result the same as what I started out with? No. Is it the opposite of what I started out with? Was this right here what I started out with? Is that the opposite of what I started out with? Written like this. It's negative what you started out with. Therefore, you've met this definition. It's an odd function. Okay, this one over here was even. And we graphed one for an example. This one's odd. Now I like to graph it, guys. So sketch. this function. A student told me earlier, on the one we just did on the left here, Professor Factor. Put this thing in factored form. I can take out a common factor of x, and you have this. I can factor a little further by a difference of squares into this. Oh, this is taking into chapter 3 so nicely. Split this up. And guys, when I do this business, which I did earlier on the previous problem, when I solve these, this is going to give me a 2. This is going to give me a -2. What am I actually finding for this particular graph when I get to it at this point? What are those 0, 2, -2? What are those? Those are my x-intercepts. Those are my x-intercepts. If I actually found the y-intercept, this was not going to be too exciting either. Find f of 0. And I think everyone in class would say, Professor, if you go back and replace these x's by 0 and do your math, you're going to end up with 0. And my y-intercept is 0, 0, x-intercept 0, 0, and also 2 and -2. Now, if I place those on the grid, I want to see what this graph looks like. And it's an odd function. Okay, guys, here it goes. 0, 2, -2. I had those as my x-intercepts. Now, I just finished this one up. That's its shape. By the way, that one over there is even. That's the sketch of an even function. This one's going to be odd. The sketch is not going to be the same. But we use the same technique. And we use sign analysis again. And see what this thing looks like. Guys, to the left of -2, I tried over here, I think, something else over here. To the left of -2, let me try -3, stay close by. Between, let's try -1. Here we'll try +1, about a test number. And out here I think we'll try a 5. And use sign analysis. Now do not let me make a mistake here. When I plug in a -3, you say, Professor, where are you going to take it? I'm going to take it right here in that factor form. Replace all those x's by -3 and pay attention to the sign. Replace x by -3, of course, out front is negative. -3 subtract 2, negative. -5. A -3 plus 2, negative. Now do that correctly? All of that together is what? Negative. Now tell me what that means happening out here based on it came out to be a negative. The graph is below the x-axis. Now where exactly it is, I don't know, you don't know, but it's below, has a little curve to it. It's not linear. Let's see if this marker will work for me. Are we saying maybe it looks something like this? It's below. Now in between, I'm trying -1. Here it goes, guys, by testing -1 here. Replace x by -1 is negative. -1 subtract 2, negative. -1 plus 2, positive. If I did it correctly. So guys, in between, with this sign analysis, it came out to be what? Positive altogether? What does that mean is happening here? Where's my graph looking? Above. Positive. Now how high it goes up, I don't know. Let's come back and pick up that. A rough sketch. On the other side, I'm trying a 1. Here it goes, try 1, replace x by 1. I see a positive. Put it in here. 1 subtract 2, negative. 1 plus 2, I guess, is a positive. Guys, if all that's correct, is that a negative altogether? which means the next piece there between these two numbers, between 0 and 2, my graph is located where? Below. So that means it's going to drop down here. How far that goes, I don't know. Does that come back up and pick that up? Yes or no?
Yes.
I'm gonna make it look a little better after finish. 5, so I'm 5 here. Positive, positive, positive all the way across. Who would think graphing's that easy? Which means it's above the x-axis out here on the edge. Do we agree? Now, to make this look a little better, I didn't scale it correctly here. There is some symmetry going on. Let me make this look a little better. Maybe like that. Change this a little bit here. Just refining this. You guys follow this perfectly. Let me go something like that. Not quite what I wanted, but does anyone see? Is there any symmetry going on here? On the last one for the even function, it was symmetric about the y-axis. One side of the y-axis to the other side of the y-axis. Is there anything going on here that I could be aware of on this graph? From one side to the other or something going on? And it's a rough sketch, it's a rough sketch. Any ideas?
X and Y.
So again,
X and Y.
wait, you're saying the x-axis?
X-axis and.
Hang on now, x-axis would take me, if I take this piece here for an example, from here to here, across the x-axis, which looks like this, would that be this piece here? Is that true? Okay. This piece is above the x-axis. Does it now fall below out here? How about the y-axis? Suppose I take this piece here across the y-axis, would this piece taken across the y-axis give me the other piece? No, so it's not symmetric at the y. The x, if I take it across the x, guys, again, I see what he was talking about here. I'm going to flip this over. Is that true? And you're going to take this up here. There's something better. Who thinks they see something else besides, this one's a little tricky, symmetry, to go from one side to the other side?
Symmetric to the origin.
Oh, to me again.
Symmetric to the origin.
Through the origin. Who would think through the origin there? That you take it through the origin. If I take this piece, guys, right here, let's try this piece here. If I take this side through the origin, might it give me the other side over here? Or if I took this through the origin, like this, might it turn into the other side of the y-axis over there? Take it through the origin. I heard to take it through the origin, maybe something like this. Just to point out where the origin is. Maybe I should not do the line, that might throw us off. But guys, the graph is being pulled through the origin. So if I pull the graph through the origin, might it go from one side to the other? If I take this right here and start pulling it through the origin, might it give me this piece over here? Or vice versa? Yes or no? Does it look like it might be pulled through the origin to go from one side of the graph to the other side? Therefore, we're going to say these odd functions are symmetric if this happens about the origin. Even functions, symmetric about the y-axis. This was easier to see. Symmetric about the y-axis, even. Odd, symmetric through the origin. Even though that rough sketch may not have shown exactly what I wanted there. It's being pulled through the origin. So that was the discussion on even, odd, which is going to take me to chapter 3 here shortly. Any questions here, guys, on this? Now, let me point out right quickly. I'm not going to graph this one. I'm going to give you another function. And I think I brought in a nice one here. No graph on this one. You'll see why we're not going to graph this. Here we go. this function looks like this. X over x squared subtract 1. Probably be about the last thing we'll discuss for the even odd. Now please, the way it looks, would you identify this function as an even function? The way it looks. This one over here, some students would tell me right quickly, Professor, it's a giveaway. The exponents are even. They're even numbers, therefore it should be an even function. Now I tested it and it was. This one had a 3 and a 1 for exponents. Odd numbers. And I tested it, it's an odd function. How about this one? Is it even, odd, or maybe neither? There's an idea. I do see an odd exponent up here. It should be a 1. And down here, an even exponent. So it might be a what then? Oh, you think it's odd? Okay, I'm gonna tell you. Some students in the past said, Professor, that's a neither. It's neither even or odd, which can happen. Let me test it here. I heard odd. Let me test for odd. Take f of a negative x. If I get the opposite of what I started out with, that's the definition, it's odd. Okay, on the left, I do it like this. F of a negative x will look like this. Replace x with a negative x. And at this point, it looks like that. That's what it looks like. Let me clean that up a little bit. This is negative x over, this becomes x squared, subtract 1. Please tell me, can I say that that result right here is the opposite of what I started out with? If it is, you guys are saying, Professor, that's the same as just placing a negative sign in front of, I'm going to put this in a different color, in front of your original function, which was this. That's true, guys? Are those two sides the same? Therefore, this strange function here is odd. It's an odd function. I'm not going to graph it. Some of my students may know what the graph looks like. I'll tell you ahead of time, it's not that. It's not that. But that was even down there. It's not that. That was odd there, yes, that was a sketch. This one has a sketch also, which we can't sketch until chapter 4. The end of chapter 3. They finally show you how to sketch something like this. Right here. Odd function, but it does have some symmetry. Should be symmetric through, when I finish it up, the origin. When I sketch it. When I finally reach the end of chapter 3 and they show you how to graph this. Now, just out of curiosity, I'm leaving this. Does anyone have some ideas about how would you approach graphing? We're not going to do it here. To approach this one over here that's odd. I graph one here, I graph one here, and now this one I have not graphed for a reason, because it's not until much later. But does anyone have an idea what you would do? Maybe some students have had some math they remember. Yes?
You found the domain.
Found the domain, and the domain in this case, x cannot be equal to positive 1, negative 1. We've got a domain here. So x cannot be a positive 1 or a negative 1, which is going to play a part on the graph. So when I get to the graph at 1 or negative 1, I can't use those 2 points. Does anyone have an idea, or maybe you remember from something? I'm just trying to get some input from you before I get into the end of chapter 3. There's a graph for it. No ideas? Good. Okay, tell me more. Bella.
About a line where you can't touch it.
To show those 2 lines down through 1 and negative 1 to show you can't touch those. What were those lines called back then? Asymptotes. You remember that word? Asymptotes? This thing would have asymptotes. I don't think I've used the word asymptotes since I've known you. If I had used it earlier, you may think I was calling you a name or something. Asymptote. Come on, asymptote. Jeez. No, that will come up later. So guys, there is a graph for it. All I know right now about the graph without seeing it is it's gonna be symmetric through the origin. Like this one was. And we'll look at that later on. Okay, I got that out of the way. Before I leave this though, and do this, then we're gonna move into chapter 3 definitely. I was very fortunate today as I erase this. One of my students just informed me, as I get to know you guys better, I'll find out things. Is the professor. I had the professor you taught here, I had her. And the first thing I asked was she saying bad things about me? No, she wasn't saying bad things about me. Had not, there's not to say anything bad. Yeah, I taught her calc and the pre-calc. Now she's teaching that. But before I get into the next part here, besides the even odd, guys, I'm gonna call this part 2, I guess. I think it's all part 1. Was it part 2 or part 3? You guys were paying attention there. Number 2, I want to sketch an unusual function. Then I'll be finished with this today. Now here's one that's very, very, very strange. And I held on to it until the end of this lesson with the even odd. Guys, your textbook calls it INT X. Not f of x, not g of x, INT X. I've seen some notation like this in some textbooks. They use this notation with brackets to represent this strange function I need to discuss. Now, your textbook uses INT, I understand why. It has something to do with integers. Watch carefully. It has something to do with integers. Can anyone tell me if it does have something to do with integers? Does anyone recall, and I'll place it in a set, the set of so-called integers in math? What numbers are considered integers?
One's from
Do it
0.
again. Someone saying something.
One's from 9.
Do it again.
One's from 9.
Tell me what the first number you mentioned.
1.
One's an integer. Is 2 an integer?
Any full number?
3?
Any full number? Yeah.
Wait. Now you've got whole numbers. 0? Yes.
Yes.
How about the negative numbers, like -1,
No.
-2,
No.
-3? Can I consider those as integers? You sure can. What can I not consider as an integer?
Fraction.
Fractions. Or some strange decimal, like pi. Pi is not an integer. So if I say 1/2, 1/2 is not an integer. 3/4 is not an integer. -2/3 is not an integer. Pi is not an integer. So integers are, he got me started, this set of numbers. It's a large set. And I'm going to list a few like this. And it's infinite on both ends. So any number you can find in that large set is an integer. 100, 100 is in there. -50, -50 is in there. Square root 2, not in there. Square root 9, in there. So that's what an integer looks like. No fractions, no, just nice, well-behaved numbers, positive and negative and 0. Now, what on earth does that have to do with this, Professor? Here we go. I'm going to give you a description. If I use the INT integer, and they're going to allow us for the x can be any real number. Right like this. X is an element of the real numbers. It can be anything. It can be anything, any real number, no imaginaries. So I'm going to place, for my first example, I'm placing inside there, since it's open, I can use any real number. Let me try 1/2. You say, wait, Professor, I thought you can use 1/2. Oh no, the x, the domain is open. It's open. You can replace inside here by any number you wish. Now, what does this mean to do with it? For this int integer. You say, Professor, it's not in that set. I realize it's not in that set. I know where 1/2 is located, but it's not in that set. 1/2 is caught between 0 and 1. Is that true? It's not in there, but it's caught between. Now, what they want you to find for 1/2, what is the closest of the integers that you can get to 1/2 and not go over? Which of these numbers is the closest to 1/2, but you cannot exceed it? You cannot go over.
0.
0 is the closest you can get and not go over. So look at this strange function, which I'll wait until the end here. This is 0. Now let's try another one here. int. We'll see how this thing operates here shortly. Let's try maybe 5, 6. Let's say, Professor, 5, 6 is not inside that set. No, but I know where it is. 5, 6 is close to 1. You guys agree? It's in there. Now, what integer? They want the integer now. What integer up here in this set, which one can you get closest to 5, 6, and again, not go over? 0 again. I'm going to throw in some different numbers here. Let's try int, integer, of, here goes, let's try 7/2. Professor, 7/2 is not in there. That's 3.5. It's out here. Of those black integers, what's the closest I can get to it and not exceed it? 3. Try another one here. int. This is going to be interesting. -1/2. Well, Professor, -1/2 is not in there. I know where it is. Located. It's here. Now, can someone tell me of those black integers, what's the closest you can get to it? -1/2, and not exceed it, not go over. -1. Try one more, then we'll sort of see what's going on here. Let's try maybe, sometimes this will happen. Let's try 6.
6.
Now, is 6 in there to begin with? If it's in there to begin with, it is itself 6. I don't have to locate it. It's in there already. If it's in there, go ahead and accept it as 6. Guys, one more here, and then we'll do something with this. int pi. You know where pi is. Pi is roughly what, 3.14? So it's somewhere in here. And the closest you can get to it, the closest of the integers you can get to it is 3. Another 3 here. And that's the way it works. This is some examples. Now you say, Professor, close down before we take a break. You've shown us, Professor, a graph of an odd function. You erased, you had an even function. This is a function. So it should have a graph. Wait till you see the graph of this. It's not a parabola. It's not one of these nice ones I just did. See what the graph of this greatest integer function is? First, get this straight here. This is a good thing to stop with. Beautiful. Before we take that break there. Guys, we set the grid up, and with your help, we're going to do this. Mr. Park, did you find those minimum values for us?
Mm-hmm.
What were they? Were they nice numbers?
It was -81/4.
Oh, we're well behaved. Was one negative, one positive, but they're both negatives.
Oh, you're asking the x value, right?
How about the y value?
The y value was negative 81/4.
For both?
Yeah.
See, it's the same thing. Okay, now guys, on this one, here we go. Help me out. Now wait till you see this strange function. I'm gonna start out from 0 to 1. I know the greatest integer value function, greatest integer function value at 0, since it's there, is 0. Anything in between, I tried a couple of things fall between 0 and 1. I tried 1/2, 5, 6. Did they also come out to be zeros?
Mm-hmm.
So that means, look at this strange graph, guys, let me keep it in black. All these stay at 0. 1/2, 5, 6, 3/8. They all have a value of 0. INT of those, and I tried a couple here, these came out to be zeros. So everything in between there is 0. Until I hit 1. Now, if anyone tell me what is the greatest integer function value at, I may try one here. If I ask you this, what would you guys say at this point that is?
1.
Is that 1? Is that in the set to begin with? So that means at 1, it jumps up to 1. Now, how about anything in between 1 and 2? Like 1 1/2? I may have tried 1 1/2. No, I didn't try 1 1/2. Let's try greatest integer function value at 3/2, that's 1 1/2. Is that still 1? So what's going to happen if you try numbers between 1 and 2? It stays at 1 until you reach 2. What's going to happen at 2? It jumps up to 2, stays there until you reach 3. And it jumps again. And it goes on and on and on like that. Let's try on the other side. Any number caught between 0 and -1. Let me see if I tried something. Oh, I tried -1/2. And the greatest integer function value at -1/2 when I tried it earlier was what? -1? So that says now over here on this side, this is open, be a function. This is inside the set to begin with, and all those stay at -1. Next, looks like this, it might be open down here, it might be closed. You start thinking about what's going on here, connect, and you get that. Now, some of us, I don't know your background, some of us may have seen some strange function that looks like this. We'll pass the vertical line test. So it is a function. Whew. That's the strangest of all functions that I think you guys need to worry about in this class. It's called the greatest integer function. It looks like a little series of steps. And some textbooks will call this the step function. Looks like a series of steps. Now, before we take a break here, if this is my function, it should have a domain and a range. Can anyone tell me what you think the domain, be careful, on this int, greatest integer function, describe it here. What do you think oh, I already said it. What's the domain, the x here? I can replace x by anything I wish, all real numbers. Now, I need, what's my range?
Would the range be the same function?
What's the range? This one's tricky. That's why I saved for the last one. I'll tell you again. Ignacio, he sees some gaps. There are definitely some gaps on this function. He says, Professor, I see this one goes down to a -2, and that is an integer. -1, that's an integer. 0, that's an integer. This is all at 1, that's an integer. This was a 2, right? Integer. So he said, Professor, the range must be what? The set of integers. In other words, this is the range. Now, so we will not have to copy this down again. This is a set of integers. In mathematics, we use this notation, just like a Z with a little line in it, to represent a set of integers. So if I see that on your paper, I'll know you meant this is the answer. The set of integers is the range. That's like a Z there for notation. Wow. Now, got 5 minutes. Can anyone tell me why would I, in my planning, wait to the end to bring this in? First is scary. It's not well behaved. Like those two I did earlier, even odds, not well behaved, it's not well connected. Strange looking function, step function. Sort of reminds me of, since tax day is coming up for me pretty soon, I owe taxes this year. Sort of reminds me of when I go in and talk to my tax person, if you make an income that's at a certain level, you pay a certain tax. If your income goes to another level, she looks over and says, oh, you're at a different level, Ramsey. You made more money this year. You have to pay more. So it looks like it's a little steps there of income. And it tells you exactly how much income tax you'll owe there based on that income. Guys, we got the domain, we got the range. Now we'll use a word here to close down. The other two graphs I did earlier, I erased them. This one's still here. Someone tell me right quickly, here's a nice, well-behaved function. This one's not behaved. What's the difference in the graphs?
Discontinuous.
That's the word I'm looking for. That's the word I'm looking for. Before I start using that word though. Someone tell me again, if you glance at this function, we did this earlier, it's an odd function. All of a sudden this strange function here, I didn't identify this as odd or even. I just called it function. Looks like this. What's the big difference in the graph, the way the graph looks there, and the way the graph looks over there?
It's not symmetric.
Tell me again.
It's disconnected.
Were there any holes on the graph over there? Quite a few here. So if it's not a well-behaved, smooth graph like over there, and it's this, the word is, this graph is discontinuous. I think I spelled that correctly. This one that's nice, well-behaved, no holes on it, no breaks on it, is a continuous. We love continuous functions. Like this, no holes to worry about, no gaps. Everything's just so smooth when you connect the points. This thing is all messed up. It's got all kinds of holes there, disconnected. Now, can anyone describe for me, when is this function, you think, discontinuous? At what values are those holes showing up? Because that's when it has breaks. I see breaks on this graph. There's a break here. 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 You try to describe to someone, when is that happening?
Z.
Yeah, is it discontinuous at every integer?
Yes.
Is there a hole there at every integer? So this thing is discontinuous at any integer. This nice, well-behaved graph is continuous for everything. No breaks, no holes, nice continuous function. Now, we got just a minute or two. I did not graph this one. Can anyone tell me, do you think, when I finally get to the end of chapter 3 where they finally show us how to graph that, does anyone see, maybe, is that function going to be discontinuous, you think, or continuous? The way it looks, as of today. They're going to discontinuous. Can you tell me where might something strange happen that splits my graph up,
Negative.
or holes, or something? At what point, over there it's all integers, at what points might something strange happen on this one?
Negative.
Negative 1 and positive 1. That's true, guys? You end up with a zero denominator? So something's gonna happen at 1 and -1 when I finally get to graphing this, later on in chapter 3. It's discontinuous at 1 and -1. This one's discontinuous at all integers. I think that's good. Does this make sense? Today is Monday, isn't it? Do we meet tomorrow?
If only.
That's, if only. You guys didn't receive an email? Did they not change the course for us? Darn it. Wouldn't it be nice to meet tomorrow also, Tuesday? Am I back in here on Wednesday? Mr. Park? Mr. Park and I could be here Thursday? Sujin, I'd give Mr. Park off and she could join me on Friday. And we'd have class Monday through Friday. And then a little casual thing on Saturday. Yeah, wouldn't it be nice? I remember back in the days I used to do that. We used to do that. I'd stay so late here, the custodians had to run me out. I had classes, I kept my classes like you guys in at what, 7:25? And some of my students said, Professor, could you stay with us a little later and work more with us? And I did. And pretty soon somebody would knock on the door and the custodian says, Ramsey, you gotta leave. We gotta clean the room and all that. You gotta leave. It's 10 o'clock. What? It's 10 o'clock. I did that many times before. Okay, guys, good stopping place? Anything at all to ask about? Now, if you did not pick up your exam, I have it. Take your 10-minute break.